Okay guys, so in the previous classes we talked about the angular velocity of an effector with respect to the base coordinate system, and we started our Jacobian matrix is the most important part of the robotics, and we derived this is end effector position and linear velocity, right? Remember, and the orientation that we got, and the angular velocity, okay. We said that the end effector with respect to the base coordinate system is velocity, linear, and the angular velocity of the end effector with respect to base coordinate system, and we said it's equal to, can decompose as this: J of V linear velocity, Jacobian of the angular part, in Q dot. Remember? So, and I taught you that the Jacobian matrix always for robotic system is 6 by n matrix, right? So, and because in the space we have 3 linear velocity of end effector and 3 angular velocity of the end effector, so this is gonna be 6 by 1, that's right. So this is 6 by n, so this is n by 1. So 6 by n multiplied by n by 1 gonna give you 6 by 1, that's right. So, and these are the velocity of the joints. This is the vector of joints velocities, okay, and this is end effector. This is for E, end effector velocity, linear angular velocity, and this is the joint. Okay, so and so this is 6 by n Jacobian matrix, and the n is if you have n links, or I'm going to say joint. I'm going to talk about this later. Joint. Okay. Fine. So because this joint goes here, n joints. Okay. When you have n joints, you have n angular. You have n velocity of the joints. That's right. So, for example, so joints, okay, this is the most correct one, not the links, because in some special cases one link has 3 degree of freedom, so you have 3 joints on that, so that's why. So example is this robot, guys. Okay, and is it recording? Yeah. And finally end effector. This is end effector n. Okay, and changing the name, so this is rotating around this axis. So as I taught you, you had in the midterm, so you will have in the midterm, so you're gonna have this z of this joint is this z naught, so this is theta 1. So, and suppose that this is the rotation is like this, right? Sorry, must be that way, the right hand rule, this way. It's gonna be theta 2, and this is z1, that's right. And suppose that this is rotation is in this way, you're gonna have theta 3 and Z2, Z0, Z1, Z2. And obviously you have an effector here. Say I'm saying Z3, okay, for the end effector. But you have how many links? You have 1, 2, 3 links, and for this specific problem you have 3 joints, right? 1, 2, 3. So the Jacobian matrix, as I'm writing here, I'm talking about this point. The Jacobian matrix has 6 rows, okay? 6 rows, 1, 2, 3, 4, 5, 6. And how many n joints? Because you want 2, 3, you have it. So you're gonna have 3 columns. 3 columns. Understand? So this is for this specific robot, because we have 3 degree of freedom robot. 3 degree of freedom robot. But accidentally, here's the number of the links. If you ignore the ground, gonna be 3 that they are equal. Okay. This is 6 by 3. This is Jacobian matrix. Now multiplied by this term, So you have that term is 3 by 1 because you have 3 degree of freedom. 3 by 1. You're gonna have theta dot 1, theta dot 2, and theta dot 3. So by this mapping, you can find end effector linear velocity and angular velocity for this specific one. I'm gonna go over it, okay, by a specific example. So J end effector respect to the base, because finally I'm emphasizing we want to find end effector Jacobian respect to the base, end effector, okay. So with respect to the base is a 6 by n matrix, okay, and the n is the number of joints, okay, or degree of freedom, say, generally speaking, okay. Now we have some rules. If joints are revolute like this one, these are revolute joints, right? Revolute, the Jacobian of each joint is being calculated by this formula, guys. Zi minus 1 cross product of end effector respect to position of end effector respect to base minus O end effector link position of link I minus 1 respect to this. That's right, joints. So Zi minus 1. Hold on, I want to give you some examples right now. If joints are prismatic, okay, the Jacobian of that joint is being calculated as Zi minus 1 and this. And finally, Jacobian of end effector gonna be calculated as J1, J2, Jn. So I is from 1 to n here. Okay, understand? So we have to calculate each joint Jacobian one by one and replace it here. This is how we calculate Jacobian of the end effector or each joint with respect to the base coordinate system. Okay, understand? So on that formulation, let me rewrite it here in summary. On this formulation, what formulation? If you have a revolute joints, its Jacobian is zi minus 1 cross product of end effector respect to base coordinate system, and that joint respect to base coordinate system in zi minus 1. And for the prismatic, this is for revolute, as I said previously, and for the prismatic you get zi minus 1 and this. Okay, and the J is, as I said, is J1, J2, and the Jn, where I is from 1 to n. For this formulation, okay, zi minus 1 is rotation matrix of that joint respect to the base coordinate system in its k component. I'm gonna give you an example, okay, in k component. Understand? And the k, remember, component is 0 in the coordinate system 1. Okay, now let us go for the example of robot, and you understand that what I'm talking about. Example: suppose you have this robot, 2 degree of freedom robot, that you have 2 joints. Let me plot it. This is, so here we go. So this is one joint, this is another joint. You set up your base coordinate system or reference coordinate system, gonna be O naught, X naught, and the Y naught. That's right. And this is one joint rotation, theta 1, and this is another joint rotation is theta 2. Now you know it. That's right. So this is as base. So both of these, they are out of the page. That's right. So the line that is connecting both out of the page is going to be x1, and by the right hand rule it's going to be y1. Now you know it. That's right. And say here is a1, the length of this, here is the a2, and this is your end effector. This is your end effector. Again, I'm putting this as x2 and y2. Let me double check about the example they had previously. Okay. So this is that we can set up our coordinate system. Again, in robotics, the most important part is to properly set up your coordinate systems. If you don't do that, you have made mistake. So again, the z of this is O1. Z of this is out of the page, right? Because this is the axis of the rotation. That's right. That generating theta 2. So the x1 must be normal to both of these and the minimum length. So must be in this line, in this x1. Using the right hand rule, your thumb showing the z1 direction. So x1 must rotate to y1. Everything is right. The same for O naught, X naught, Y naught, and for the end effector. This is pretty straightforward. So because you have 2 degree of freedom system, or you have 2 joints here, planar robot, so your n is 2, right? So your Jacobian must be, that I'm gonna calculate now, 6 by 2. So this 2 comes here. 6 by 2 your Jacobian. Now I want to divide it. I want to see how can I translate the velocity of the joints to the velocity of the end effector. Okay, so your J Jacobian matrix gonna be J1 and the J2. So what we're gonna do, I'm gonna calculate each one by one, as when you have to do in the final exam, and and after graduation as a robotic engineer you have to do for the specific robot in your company or in your research center, okay, whatever. So this is 2, J1 and J2. So okay, let's do that. It's gonna be a time consuming process, so we have to do it. Okay, so for example, your J1, based on the notation that I had here, look at here, and the both are revolute joints, so I'm gonna use this formula. So J1 gonna be Z I minus 1 is 0, Z naught cross product of O of what? O of 2, and the Effector here. That's right, O2, because we assign the coordinate system number 2 here. That's right, O2 with respect to base minus OI minus 1. I was 1, so it's gonna be 0. O0 with respect to 0. And here again, I minus 1, I is 1, so we're gonna be Z naught. Here we go. You have to do the same. And J2 is Zi minus 1, I is 2, gonna be Z1 cross product of again O2 with respect to 0. Here we go. Yeah. This is constant here. And now OI minus 1, I is 2, I is 2, gonna be O1 with respect to 0. Again 0. So now we have to calculate this one by one. Understand? But I taught you, if you remember previously, transformation matrix, right, of 1 with respect to 0, coordinate 1 with respect to 0, 1 with respect to 0, and 2 with respect to 0, and transformation of 2 with respect to 0. And we know that transformation is 1 with respect to 0, 2 with respect to 1. I taught you this, and I'm pretty sure you had in your midterms, right? So now let us calculate this one by one. One by one. So because I have to find this from here, 2 with respect to 0, 2 with respect to 0. How? Bear with me. Okay, and O1 with respect to 0 from this 1 with respect to 0. Let us do that. So T1 with respect to 0. As you know, you have a 4 by 4 matrix. Remember? Here we go. 0, 0, 0, 1. Now you have to say hold on guys, you have to say, look at here, now you know it. Coordinate 1 with respect to x1 with respect to cosine theta 1. I'm doing with you one by one. Cosine theta 1. x1 with respect to y not gonna be sine theta 1. Sine theta 1. And there's no component of that here. Now y1 with respect to x not gonna be minus sine theta 1. On the hand you transfer it here, that's right, minus. So gonna be cosine theta 1 and 0. And both these z1 and z0, they are parallel, so you're gonna have 0, 0, 1. So this is that. Now this is for rotation part of that, that's right. This is what rotation matrix part of that. Now about the displacement, that's right. So this is displaced with respect to this coordinate system. How much? This much. This much. how much? A1 in x direction, A1 cosine theta 1. That's right. Gonna be A1 cosine theta 1. Yes. And A1 sine theta 1 from trigonometry. A1 sine theta 1. What about the z direction? Any transformation? No. So this is 0. We got it. That's right. So this O1 respect to this, if I want to become more accurate, you have to just get it from here. Bingo. Understand? Huh? Yes. So, and this Z1, let me change the color. This Z1, Z1 I said is what? Z1 is what? Well, let me first go with this. Or this Z0 is what? Is this element. Here we go. Okay? Understand? Because as I taught you here, has a reason. Z I minus 1 is this. So Z0 is R0K. Look at here. Z0 is R0 respect to 0 in K. That's right. R0 respect to 0 is unit matrix. That's right. Multiply 0, 0. Here we go. It is 0, 0. Understand? So, and now Z1 respect to Z1 is R1 respect to 0 in K. So this is R1 respect to 0. I'm just putting here, guys. Cosine theta 1, sine theta 1, 0, minus sine theta 1, cosine theta 1, 0, 0, 0, 1. In K, your K is what? Your K is 0, 0, 1. So you're gonna have what? You're gonna have again 3 by 3, 3 by 1. So you're gonna have again 0, 0, 1. So this also stands for both of these. You got it? Based on exactly whatever I taught. And this is 0, 0, and 1. So we got these. We got these. I got this. Now I have to calculate this, because O0 respect to O0 is 0, no doubt. That's right. Displacement of coordinate this respect to 0. That is 0. We don't care. So now only unknown is this. So unknown is how we calculate that? By this. So T2 respect to 0 is 1 respect to 0 in 2 respect to 1. So 1 respect to 0, we have it here. Here we go. Cosine theta 1, sine theta 1, 0, 0, minus sine theta 1, cosine theta 1, 0, 0, 0, 0, 1, 0, A1 cosine theta 1, A1 sine theta 1, 0 and 1. Now T2 respect to 1. T2 respect to 1. We have to look at this figure. Coordinate 2 respect to the coordinate 1. X2 with x1 gonna be cosine theta 2. Cosine theta 2. So x2 respect to y1 gonna be sine theta 2. Sine theta 2. The both these, they are out of the page, gonna be 0, and you know this is 0, 0, 0, 1, right? So now y2 transfer it here. Respect to x1 gonna be minus sine theta 2, minus sine theta 2. y2 respect to y1 gonna be cosine, oh, what happened? Cosine theta 2, 0. The both are parallel, 0, 0, 1. Now it's transformed, so this is transformed in this value. Let me show you. I want to magnify. It's transformed in these values. Oop, these values. How much? A2 cosine theta 2, A2 cosine theta 2, A2 sine theta 2. What, z? No, there's no z. Understand? Huh? Understand? So if I multiply these two to get this one, to calculate this one or this one, okay, so I get this. Let me go to the next page. I get this. T2 respect to 0 is I have in my a piece of paper, I have done that, is cosine 1 2 sine 1 2 0 0 minus sine 1 2 to save your time. Cosine 1 2 0 0 0 0 1 0 a2 cosine 1 2 plus a1 cosine 1, so a2 sine 1 2 plus a1 sine 1 and 0 and 1. Okay, in this notation, for simplicity and saving the page, cosine 1 2 is cosine of theta 1 plus theta 2, and the sine 1 2 is sine of theta 1 plus theta 2, and the cosine 1 is cosine theta 1, sine theta 1, and you know this the rest. So now this is what? Now this part, as I taught you previously, showing O2 respect to 0. Understand? Okay. Now let us calculate the Jacobians one by one. J1 is Z0 cross product of O2 respect to 0, and this is 0, obviously, because there was displacement. Understand? And Z0. So again, from here we got that. Z0 is 0 0 1. I'm writing here, guys. There's no magic. 0 0 1 is Z0. So J1 is first of all, before going to J1, I have to calculate this. Z0 cross product of O2 respect to 0. O2 respect to 0. So this is Z0. Z0 is how much? Z0 is 0 0 and 1 in cross product of this part. A2 cosine 1 2 plus A1 cosine 1. A2 sine 1 2 plus A1 sine 1 and the 0. And from the high school, you know that the cross product of two vectors is being determined via this determinant ijk unit vectors, 0 0 1 the first vector and second vector, which is A2 cosine 1 2 plus A1 cosine 1, A2 sine 1 2 plus A1 sine 1 and the 0. So this is equal to I in determinant of 0 1 a2 sine 1 2 plus a1 sine 1 and the 0 minus j cofactor 0 1 a2 cosine 1 2 plus a1 cosine 1 and 0 plus k in determinant of 0 0 a2 cosine 1 2 plus a1 cosine 1 a2 sine 1 2 plus a1 sine 1. This is 0, no doubt. So what you get is this minus a2 s1 2 plus a1 s1 in I side plus a2 cosine 1 2 plus a1 cosine 1 in j plus 0 k. This is for this word. Understand? So you can write it as a vector minus a2 sine 1 2 plus a1 sine 1 a2 cosine 1 2 plus a1 cosine 1 and 0. But this is the first line of the Jacobian matrix. Yeah. We have a second, which is 0 0 1. So Jacobian 1 J1 so J1 becomes 6 rows first for J1 gonna be minus A2 sine 1 2 plus A1 sine 1 A2 cosine 1 2 plus A1 cosine 1. I'm just replacing here from here. Here we go. The first line. 0. Now Z naught. Only Z naught. 0 0 1. This is Z naught. This is Z naught. And this is what? And this is Z naught cross product of O2 respect to 0 minus O this respect to 0. So bingo, we got J1. Understand? We got J1. So now we have to go calculate. See the time. Yeah. We have to go J2. J2, as we calculated, Z1. Here is R1 with respect to 0. This is like at the Z naught. For this specific problem, guys, is like that. For different problems, must be completely different values. Okay, don't think that this is planar robot. Okay, on the page. Okay, so we're gonna be 0 0 1. So we have this. So O2 with respect to 0, we calculated that. Where is that? Where is the O2 with respect to 0? Yeah. Here's O2 with respect to 0. We calculated that. So what we need? We need here we go. O1 with respect to 0. So O1 with respect to 0, we calculated that. This is O1 with respect to 0. Here we go. That's right. So now first I'm gonna calculate this. So Z1, look at here, guys. Let me change the color. I'm done with this part. So I'm going to Z1 cross product of O2 respect to 0 minus O1 respect to 0. So Z1 is, as we calculated, is 0 0 1. Cross product of O2 respect to 0. O2 respect to 0 was A2 cosine 1 2. Here we go. Let me show you. A2 cosine 1 2 plus A1 cosine A1 plus A1 cosine A1. A2 sine 1 2 plus A1 sine 1 0 minus O1 with respect to 0. We calculated O1 with respect to 0 from this transformation. A1 cosine theta 1, A1 sine theta 1, 0. Gonna be A1 cosine theta 1, A1 sine theta 1, and the 0. Here we go. So you see that this with this goes, and this with this goes. So what you get finally is this 0, 0, 1 in cross product of A2 cosine 1, 2, oh, A2 sine 1, 2, and the 0. So if you do that as we did I, J, and K, 0, 0, 1, A2 cosine 1, 2, A2 sine 1, 2, and 0, what you get is, I have in the piece of the paper, minus A2 sine 1, 2, A2 cosine 1, 2, and the 0. Bingo. And we know that J2 is Z1 multiplied by O2 respect to base coordinate system O1 and Z1. So you can simply say J2 is, we got this here, minus A2 sine 1, 2, A2 cosine 1, 2, and 0, and Z1, 0, 0, 1, 1. This is 6 by 1 again here. But we have 2 degree of freedom robots. So the Jacobian matrix finally, as I taught today, the Jacobian matrix is J1 and the J2. So it's gonna be minus A1 sine 1 plus A2 sine 1, 2, A1 cosine 1 plus A2 cosine 1, 2. This is bracket 0, 0, 0, 1. And now minus A2 sine 1, 2, A2 cosine 1, 2, 0, 0, 0, 1. Obviously, this line is J1 and this line is J2. And the totally is Jacobian matrix of this planar 2D graph freedom robot that is transferring, that is this 6 by 2, that theta dot 1, theta dot 2. It's gonna be 2 by 1. This is gonna give you x dot in x direction, y dot in, oh sorry, let me rotate this, v in x direction, v in y direction, and v in z direction, omega in x direction, omega in y direction, and omega in z direction. This is for end effector, and these are for the joints, and these are for the joints. Here we go. So you have 6 by 2 matrix that transferring the joints velocities to end vector velocities in space. No doubt that Vz gonna be 0, right? Because this is planar. There's no velocity in the on this direction, right? Understand? So now I'm giving you an assignment for tonight. Judge about these angular velocities. Which of them are 0? Which of them are 0? omega x is 0, omega y is 0, omega z is 0. You have to judge it. Okay? So next week, next class, I'm going to talk about redundant robots in the continuation of the Jacobian matrix, like the Baxter 7 degree of freedom robot I am in lab.